I'm glad Rick already gave this beautiful talk about EIC science. Of course, there's no way to improve on this. So what I'll do in my talk is, again, change the perspective a little bit. I will talk about eRHIC, but I will also try to start the discussion about how actually a program at an electron ion collider might work. So let me begin here with the outline. First, some recent updates on EIC science from the Brookhaven perspective, eRHIC design, eRHIC Accelerator Detector R&D, and then program considerations. And I'd like to thank all of those who helped in putting these slides together. And I can't mention everybody, but these are the main people. So the case for the EIC really was made explicitly in two important documents that we now have in hand. One is the long-range plan with its recommendation that a high-energy, high-luminosity polarized electron ion collider should be the next facility that the nuclear physics community wants to construct after eRHIC is complete. And then more recently, the report from the National Academy of Sciences that essentially makes the same statement, although it doesn't talk about the next nuclear physics facility, but it describes that the committee finds a compelling scientific case for such a facility and that the science questions are central to completing the understanding of atoms as well as integral to the agenda of nuclear physics. But it goes on and says that the development of an EIC would advance accelerator science and technology in nuclear science, and it would benefit other fields of accelerator-based science and society for medicine through material science and elementary particle physics. And I think on a broader scale of getting an EIC built, these are very important components that we need to keep in mind. So what the National Academy report really emphasized and confirmed is the breadth of the science case that goes from the precision mapping of the internal structure of protons and nuclei to the exploration, discovery of undiscovered phenomena at high density and in areas of proton and nucleons and nucleus structure that have not been investigated in detail before. But also, as I mentioned, that the EIC will drive technical innovations and support societal applications, which make it an important tool from a national point of view to build. So in a sense, you could say, this is where Abe's talk ended. The justification phase for the electron ion collider has ended. It's complete. We have documents from the nuclear physics community and from the national science community that clearly make that case. This is really all the DOE, the Office of Management and Budget in Congress, need as information to justify funding the construction and eventually operation of an electron ion collider. So you could say we're entering now the realization phase. Now, no project gets realized by itself. It's only if the community that wants it and supports it stays united and focuses in the right way of getting it realized. And so what we'll need to be able is to state the science case as crisply and as compellingly as possible. And what Rick said was clearly a piece in that communication. We need a credible facility design that can be successfully built and operated. And both Jefferson Lab and Brookhaven have been working very hard on this over the last few years. We need a plan to realize the science goal when the EIC is completed and maximize the return on investment. And that's one consideration I want to bring in later today in my talk. And finally, we need to attract the widest global community of users, and the EIC user group has really made a lot of progress in that direction. And when you go to Europe, you even see that there is quite a lot of excitement and interest in this. And so this INT program is one of the many steps on this path. And as you think about what will be the eventual fallout of the legacy of this program, you have to think about it in terms of how can it help in the realization phase of the facility. So next I want to show a few slides about the science recent science updates. Many of you may have seen those before, but it's useful to repeat them. So when we reconsidered what really is the science case for the EIC and how does its energy and luminosity range play here last year, this is a diagram that really helped guide the thought. Namely, a diagram, a QCD landscape diagram, where on the one axis you have the resolution and on the other hand, on the other axis, the parton density. You can think of this as the Q squared variable and here as the variable 1 over x. And there are many areas that have been widely explored, but they're clearly areas which need further exploration. There are the areas where detailed investigations and precision mapping will be necessary, but here there are also unexplored areas where discovery can and likely will happen. So the EIC really is able to put more details on that landscape. And so here is this document that was put together by, in particular, Elke and Raju and Thomas Ulrich and others last year. I know quite a few here contributed to this, which made a reassessment of the relevance of the energy range that was specified in the long-range plan and now has been confirmed in the National Academy report. And the conclusion was that really this was the right energy range, and it was important to have that energy range to realize all the potential of the EIC. And the following slides show some examples. One was the determination of the various components to the proton spin. And as you have the full energy range of the electron ion collider, you see that you can actually, in the end, determine the different components to precision that really makes a difference on the level of 1/2 h-bar. When you ask the question, what about the gluon structure of nuclei, then again, what you find is that in order to determine the gluon structure in nuclei over the range of both the RHIC and the LHC heavy ion program, where heavy ion physicists would like to understand better what is the structure of the colliding nuclei, you see again that you need the full range in order to get down into the full energy range of the LHC. There's been a lot of work in the last few years coming from RHIC and from the LHC about the gluon structure and the fluctuations in the density of protons, mostly coming from proton-nucleus collisions, but also proton-proton collisions. Here is a simulation of what the density in a proton may look like based on theoretical assumptions. And to study this really, again, it's really important to have the full range. And finally, when you ask the question, what do you need in order to get into the domain of high gluon density, where nuclei become opaque, then again here it is the full range that is necessary in order to actually see the change from a dilute into a dense regime that is encoded in the theory of gluon saturation. So the conclusion from this was what had come out of the discussions of leading up to the long-range plan was the right energy range, and this then also made it into the Academy report. So let me next talk a little bit about the design for the electron ion collider. Okay, eRHIC. We reconsidered this about 2.5 years ago because it became clear that if you actually want to realize a facility that the funding agencies are willing to construct, they have to have limited risk, but at the same time promise the full performance that the science requires. And so we went back to a design that said, let us look at a solution of a storage ring. And as you know from Abe's talk, this started out in 2000 with the consideration of the storage ring. And so we went back to this and actually asked the question, how far can we get? Can we really fulfill these requirements that the consensus documents have achieved? So this led over the last year and a half to a pre-conceptual design report. If the document that came out of the 2010 program here was thick, this is even thicker, it's about 800 pages. And describes in all details how you would actually, in detail, construct such a facility. And the conclusion is that it is actually possible with very modest risk, based on very modest extrapolations of what is state-of-the-art in accelerator technology. It is possible to build a storage ring-based electron-ion collider that satisfies all these requirements in terms of polarization, in terms of ion beams, in terms of variable center of mass energies, and collision luminosities. So in order to reach the full 10 to the 34th per square centimeter second in luminosity, one needs strong Hadron cooling. I think everyone who's looked at this agrees with this. But it is possible to get to about a factor of 2 of this without this still unproven technology.
What's strong Hadron cooling?
Strong Hadron cooling means Hadron cooling on a time scale that is of the order of an hour. Okay. Now, cooling is typically takes many hours, but if you want to go to an hour or below, that's really very strong cooling. And so the Brookhaven design is based on the RHIC complex with the storage ring, injectors for the electrons, the existing heavy ion injectors, the sources, the infrastructure, and so forth, with relatively few modification to the ion part of the complex. It adds a 5 to 18 GeV electron storage ring and the ejectors that are necessary to reach that range of center of mass energies. It's optimized under the assumption that each field will have the parameters that have been demonstrated collisions in other colliders. That is what minimizes the risk of the construction. It turns out when you think about this, in order to have a adaptable polarization in the electron beam, what you actually need is to have the variable spin pattern. You require on-energy and spin-transparent injectors so that you can inject the right electron polarization into the storage ring. And then the final consideration is how much synchrotron power do you want to actually allow? And we have put a design limitation of 10 megawatt, which basically limits the combination of energy and intensity in the electron storage ring. That's a design choice. You could go to 20 megawatts and you would increase the parameters. But on the other hand, we live in a time when actually energy consumption is an important consideration, and so this is what we chose. So the key additional components to the existing RHIC complex are an electron injector synchrotron. That is a synchrotron that actually accelerates the electrons to full energy and then injects them into the storage ring. And this can be done with a synchrotron that fits into the RHIC tunnel. We have an electron storage ring. This is the injector and the storage ring here, these two additional rings in parallel to the existing 2 heavy ion rings. And finally, the interaction regions for the detectors, which are very complex animals that actually have a lot of sophisticated design in them in order to obtain the full luminosity and experimental conditions that are required for the experiments. So I won't go through this in detail because mostly we have here theorists, not accelerator scientists, and some experimentalists, but not accelerator scientists. But all this laid out in great detail in this document. This shows the RHIC layout, and how in the existing RHIC ring with its 6 straight sections, we would put the various components. So we usually call this in terms of the clock, 12 o'clock, 2 o'clock, 4 o'clock, 6 o'clock, 8 o'clock, 10 o'clock, straight regions. Here at 6 o'clock and 8 o'clock are 2 large detector halls that serve for star and phoenix, and which would be reutilized. Here at 4 o'clock is where the Hadron injection and RF power are. Here at 2 o'clock is the electron injection and the polarization instrumentation. Here we have polarimeters, the snakes that will actually maintain the polarization in the ring, and RHIC we now have 2, but to accelerate and store other ions like deuterons and helium-3 polarized, we need 6 snakes. And then finally here at this point are the electron radio frequency acceleration and also the cooling and the beam dump would be installed. So this fits all very nicely into the existing facility. The main technical challenge, if you really want to go to 10 to the 34, is strong hadron cooling. It's required in all schemes for electron ion colliders. And several methods have been studied, and we've looked at them again. There's bunch beam electron cooling with an electron storage ring, and coherent electron cooling with an FEL amplifier or micro-bunching amplifier. At this point, since none of these have been explicitly demonstrated, we consider the most promising approach to be micro-bunched electron cooling with 2 so-called plasma amplification stages. This requires 100 milliamp electron current. When you think about this, this really requires an energy recovery linac, and with flat beams, one gets cooling times of the order of 1 hour, which is sufficient to reach that luminosity at eRHIC. But it's also clear, as already Rick has emphasized, that substantial R&D is needed before such a facility could actually be constructed and realized. But there are no fundamental obstacles to that we know of.
Has it ever been tested? Has it ever been tested?
Well, it has never been fully tested. But at this point, it is based on simulations. The first bunch beam electron cooling we currently commissioning at RHIC, so the beam energy scan 2 and low energies. This will be the first implementation of bunch beam electron cooling. But it will be the traditional electron cooling, not the one where you actually amplify using coherent amplification techniques.
So there are 2 techniques, different techniques. So bunch beam cooling, there has been some amount of demonstration being done in China already. But as I said in my talk, it's actually not really required for the coherent beam cooling. I think it's fair to say it has not been actually demonstrated. There's theoretically possible simulations.
Yeah.
Some simulations. I don't think that has been demonstrated.
No.
We need to do that.
Is always the problem there. For some of the pieces to really test it, you need almost an electron ion collider. So DC cooling has been done at some level at Formula and at COSI. We at least have done the stuff that we can show more that there's nothing intrinsic from DC cooling to bunch beam cooling. But in the end, the real things of the beam cooling we all are after, at some level, needs quite some infrastructure. So this is the problem.
Sorry, just a question of the ignorant theoretician.
Yes.
I mean, I guess that the limit you have on the synchrotron radiation has also an impact on the maximum luminosity. So this 10 megawatt. Sure. So how large is this impact? Because one could gain some. The question is, can you gain something in releasing this 10 megawatt limit or not?
You could gain something.
It goes linear because it is a bunch current. So the luminosity goes linear, but of course the cost to compensate for your losses with synchrotron radiation go with the cost of electricity, which is not linear. That is
Okay.
like slightly maybe
So-
more exponential or dipole function, who knows?
I was just wondering
Yeah.
if one, because I always hear talking about the Hadron cooling as the crucial
Yeah.
ingredient, but I was just wondering if you can work on the electron side.
It's also at the
Yeah.
highest
Higher.
maximum. So it's the highest B
right.
energy. So in the middle is gravity.
But I mean, the radiation goes like the fourth power of the energy. And so you really, even if you allow for a factor of 2 more in synchronous radiation, you don't get very far. Okay. So,
So sorry.
yes, go ahead.
Now that you show this plot, so the luminosity and annual integrated luminosity correspondence in this plot implies that essentially the luminosity you quote on the left side is exactly the same as what I discussed in my talk. Namely, the average luminosity while the thing is
Correct.
Yes.
That's
Yeah.
correct.
And also operational efficiency.
Operational.
So what we have.
So we're talking about the same thing.
Yes.
So when you look at the peaks here, 10 to the 34 with strong cooling, 4.4 times 10 to the 33 without cooling, it's very similar to the numbers that RHIC showed. And they simply show that there are fundamental limitations in accelerator design that come into play.
The only difference is always like whether you assume a snow mass yield with an efficiency of 70% or you assume during half the yield an efficiency of 50%.
So I think that was 10 to the 7 seconds in this plot.
Yeah.
And some plots have that also written, so indeed it depends a bit what you assume for the year.
It's the same.
Yes, but the rest was the same.
We have someone higher.
So we've also thought a little bit about a timeline. We have currently plans for the RHIC science program to extend through a run in 2025. First the beam energy scan and then the S-Phoenix runs over 3 years. We would need about 3 years of access to the tunnel to install all the components, and so commissioning could be starting in 2029 and real operations sometime in 2030. So that's a technically driven schedule, and obviously not one that is actually driven by how funding is available. That could change things, and very likely will change things, although that's something we don't have any control over at this point. That's an issue for the funding agency. So in order to realize this, of course, there's a lot of R&D that's going on. Last year, the DOE started an official Electron Injector Accelerator R&D program. That's a national program with $7 million of funding. Was actually, to a large extent, taken out of operating funds at the labs, some additional funds, and now has supported quite a few projects that are mostly collaborative, as you can see here, on Korean electron cooling, development of simulation tools, studying spin transparency, crab cavity design, high gradient active shielding quadrupoles, which is very important for the interaction regions, development of helium-3 ion source polarimetry, and so on. So there's a lot of R&D that goes on and is currently funded, which is necessary to bring this from conceptual design to actually constructible designs. But none of this, except with the possibility of coherent electron cooling, is seen as potential showstoppers. I won't say much about detector R&D. We don't have an official national program yet. We have the program that's run out of Brookhaven by Thomas Ulrich. You've seen these different schematic designs of detectors. And it's clear that what is really important is to think about what are the measurements that we think need to be done and how we actually want to arrive at the detector designs and make choices and think about what are new technologies that have to be developed or which are technologies that have to be improved in order to provide the optimal science capabilities that will be needed. So let me end with some considerations about how actually one should begin to think about an actual science program. The reason why I think this is important is because if that schedule that I showed you actually is realistic, then we need to begin to actually have conversations about how to design and build detectors, because if you want to have a detector commissioned in 2029, it becomes really soon important to begin conceptual designs of those detectors. So the first thing to think about is that colliders typically start gradually. Even if you have a design luminosity goal of 10 to the 33 or 10 to the 34, or whatever it may be, when you turn a collider on, you don't have it in the first year. It will take several years to get there. And this is a plot graphic that was put together by Wolfram Fischer that actually looks at all the colliders in the past, starting with the intersecting storage rings at CERN. And you see that over the course of their lifetime, the luminosity has increased by an order of magnitude, sometimes 2 orders of magnitude. This is due to the fact that, first of all, the accelerator physicists have to learn to actually how to focus the beams efficiently and make them stable long enough to reach that average luminosity. But secondly, also because typically during a lifetime of a collider, there are many technical innovations that actually improve the luminosity considerably. And so, for example, for gold-gold collisions at RHIC, the facility is now running at almost 50 times the original design luminosity, because over the years, many additional technical innovations have been put into place that raise the luminosity. So when I asked Wolfram, what do you think the luminosity for an electron-ion collider would look like, he produced this curve. And of course, where this starts in time is totally up to the funding agencies. But I think this is not an unreasonable guess that over the first 5 to 6 years, the luminosity that actually will be available will decrease by an order of magnitude. So this is a table that is actually now based on our current eRHIC design, which shows what may be the initial operation. When I say initial operation, we're talking about year 1 and 2 maybe. The goal here for for average luminosity over a store would be close to 10 to the 33 per square centimeter per second. And then over a few years, as the accelerator physicists learn how to really optimally operate the machine, this would raise up to about 4 times 10 to the 33. And if you want to go to 10 times 10 to the 33, you will need, this is the normal design goal, the strong hadron cooling that I talked about. So this is the kind of expectation that one might have conservatively. Ideally, things could get faster, but this is what one has to fold into a physics program. So when you look back at existing colliders and ask the question, what are the typical operations modes? There are really 2 fundamentally different models for hadron colliders. One is the LHC model, as I would call it. In the case of the LHC, what you have is multi-year runs that are separated by long shutdowns that allow for major upgrades. So typically the LHC has run for 3 years, maybe 4 years, in the same configuration for the machine and for the detectors. Then shuts down for a year or 2, or maybe even 2.5, and does major upgrades. This suits very well the LHC case where you have a dominant run mode, proton plus proton, and the goal of the scientific community is to accumulate as much integrated luminosity in that single mode as possible. So it's really luminosity consideration for a single dominant mode that drive this operation. And then there are secondary programs like proton nucleus or nucleus-nucleus with limited luminosity. On the other hand, you have the RHIC model. In this case, the collider has actually operated every year since 2000. No long shutdown. In part because Congress wants operating facilities. CERN is a little bit less sensitive to that because of their governance model. RHIC has run multiple systems during many years, often at multiple energies. So it's not had one dominant mode that you run and then a few other modes. RHIC has worked with annual incremental upgrades to the collider during the time when the facility didn't operate, and to the detectors during these 6-month shutdown or maintenance periods. So there has been an improvement in the performance year after year, and not only in 3 to 5 years installments. And finally, various systems and energies were revisited as the luminosity increased. The detector systems acquired new capabilities, but also as the physics result from the previous run drove new questions. And one question that I think is worth thinking about, or to begin at least thinking about, is what is the right operations model for the EIC? Is it closer to the RHIC model or the LHC model? Or will it be a totally new model that we don't know yet? What is it that can bring the most physics in the fastest way out of the science program? Because once we fund the $1 billion facility and operate it, Congress will want to see optimal results as quickly as possible. So it's not too early to think about what EIC science program should be in the first 5 years. What are the most important physics questions that can be addressed as the luminosity ramps up? What are the detector capabilities that are required to carry out the measurements? And you don't need the detector capability that you need for a measurement in year 5 to be present in year 1. And depending on the model of how you operate the machine and how you improve the machine, this is a very important question. Which collision systems will have the largest impact? Which collision energies will have the largest impact? And what are the trade-offs? So in other words, given the constraints of how you bring up a collider in terms of its operation capabilities, what is the best way of structuring a physics program to make optimal use of what you have at a given moment in time? To give you an example, that early results can be obtained without having integrated luminosities of 100 inverse femtobarn. This just looks at one particular plot from the EIC white paper that is for 10 inverse femtobarn. This would be the structure function f of x in the generalized power distribution function they get out of DVCS measurement. If you only have one inverse femtobarn, the statistics is much worse, but you still get a very interesting result. It just is a lot less precise at small impact parameters, but you get a very nice result of the overall distribution. So the question of what it is that you want from the initial program is a very important one, because ultimately that will be the deliverables of the machine. Let me end with a physics question that came to my mind on the weekend. And it may be a completely crazy question, but maybe it's something to think about. So last year, at RHIC, we ran 2 isobar systems, zirconium-96 and ruthenium-96, in a comparison run. We switched shift by shift between the 2 systems. The first time the collider has operated in such a mode. And we recorded 3 billion collisions for each of these systems. Now, there was a specific physics question why we wanted to do that, and that is we wanted to explore the influence of the magnetic field generated by the colliding nuclei on electric charge fluctuations, which are a rare signal of the current magnetic effect, with a 5% precision. And this makes use of the fact that these two systems differ by 10% in their electric charge of the colliding nuclei. So that means a 10% difference in magnetic field. Since the experimental observation depends on the square of the magnetic field, there's about a 15 to 20% difference in the observed signal. And we wanted to measure that 50% difference with a 5% precision. That's why we needed 1 billion, or in this case, 3 billion collisions that actually accumulated. Now, when I look at these two nuclei, zirconium-96 and ruthenium-96, they differ by 4 charges. That's a 10% change in the electric charge. But when you look at the isospin, the third component of the isospin, it's -8 and -4, so it differs actually by a factor of 2. So the difference in isospin is actually 5 times larger, the relative difference, than the electric charge. And so one question one could ask, for example, and theorists might want to think about this, if you would compare electron zirconium and electron ruthenium collisions, would this enable certain measurements that we don't know how to do otherwise? In terms of measure the effect of the valence quark isospin distribution on Proton distributions at small x, or at intermediate x. So these are the kind of things you can do with a universal electron ion collider. When RHIC was constructed, nobody ever dreamed of doing such a measurement. But in the electron ion collider, it will be possible. So there are possibilities of looking at interesting systems that are allowed by the complexity of the wide variety of nuclei that may actually help address some interesting physics questions. So, summary, over the past year at RHIC, we've made significant progress in understanding the role of the energy range. We've completed a pre-conceptual design report for the ring-ring version of eRHIC, and we've engaged in a broad program of EIC Accelerator and Detector R&D in close collaborations with many other institutions. We are now confident that the energy and luminosity range of eRHIC would enable a robust physics program that addresses all the goals of the 2050 and SAC long-range plan. And with that, I end my talk. Thank you.
Slide 29. I don't need the theories. I can answer it.
Okay.
So the answer is yes. Essentially, if we can either by parity correlation or by neutral charge coefficient, you actually can look at calcium-48 or using these kind of different isospin. You learn this indeed like the isospin depends on the nuclear EMC effect. So you can. What you need to do is you need either to have luminosity, so you can almost have different sensitivity down quark to parity correlation, or to charge and neutral quantum. It's still, I think, one projection simulation we should do.
Yeah,
so yes, the answer is yes.
You should do it. Thank you.
Actually, next week, I don't know what the peer is talking about this, but he is actually thinking of electron measurements, so W measurements in nuclei, because they will help to construct such a system.
So again,
yes.
I mean, this has just not been worked out yet. But
True.
We had a proposal that felt put that there is really difficult, but the EIC actually could help.
Yeah.
So yes.
Actually, now I have a senior moment. Tony Thomas has actually talked about something like that, particularly electronic.
You want to understand this?
So electronic means parity violation, or it means W boson.
W boson. Yeah. He puts that forward as a very good observable to look to isospin violation.
You need to get a conflict to the proton and neutron. You need to use that to get the separation.
Okay.
Good.
How in the long-term perspective, any discussion about the possible upgrade of the proton rings, increasing energy?
So this is actually an interesting question. As you know, we have 2 rings. We really only need 1 ring for eRHIC. You could imagine at some point actually taking the second ring and replacing it with the famous 12 Tesla magnets, which don't exist yet, but at some point, hopefully they will. And that would allow basically a quadrupling in the energy of the proton. So we could get close to a TeV protons, and in the center of mass, that makes about a factor of 2, right? Now, you want to install 4 kilometers worth of dipole magnets into the tunnel. It's an expensive enterprise, but if the physics drives it, I think it's possible. Right? So I think one could, in principle, get close to about 300 GeV in the center of mass, especially if one pushes even the electron energy a little bit further. But quite recently, I think this is at least $500 million of installing 12 Tesla magnets into a ring.
Yeah, I was thinking mainly to the electron ion program, the possibility to see the saturation setting up. If you are at the edge, it's something that they probably have to consider.
I mean, if it is, if the physics drives it, it's something that's conceivable. At this point, I think it's premature, seriously planning it.
Planning is something, thinking and having options is something else.
Yeah.
Can you go back to the luminosity growth of the mission? So the thing that was a problem with Hera was that it was a big success in many ways, but it was a kind of a failure in another way, which was that expectations at Hera were much higher than the actual luminosity delivered. So in some sense, that entire curve of Hera 1 never really achieved the expectations that we had when we first started that program. The studies that we did were kind of an order of magnitude expected, and not kind of an order of magnitude. In fact, the Hera 2 upgrade barely got there. So in that sense, the luminosity growth was really
What was the problem? Was beam target time?
So I don't quite understand this. So when we started the machine, we expected something to accumulate something like 20% picobarn per year. We got 40 meters now. Now I don't quite know, looking back in history, whether this was a communication problem between the physicists and the accelerator physicists, or there was something really wrong. But I'm telling you that this was really an issue.
Yes.
And we were lucky that low-X physics was there to do something.
Yeah. If you had to do it on that quarks.
Yeah. Yeah. So we want something much more like the IC that shoots up immediately. And unless we are in the presence of some other rock, I think we want the curve to look much more like that than to be honest.
Yeah.
And the problem, of course, is that we have a very wide physics program, and only a small part of it can be done with zero luminosity. So that means a big chunk of things cannot be done for 5 to 10 years. This is, to me, an enormous problem. So I think we really need something that actually looks much better than that.
First of all, accelerated technology and simulations have made a tremendous progress in Sarah. So I think one needs to take that into account. The other aspect is it's important for a new facility not to raise expectations that then get disappointed.
Yes, but
right? Especially in the US system where anything that is a disappointment is will be resented at various levels.
Well, talking about politics, it will be success by definition, of course, but we're talking about science here. Right?
Yes.
So if we're serious about doing the science that we want to do, then we need to get a machine that actually will do that science. And I think if we're not going to get that machine, then we have to do it now.
if I heard you right, you're just arguing about the slope of that increase. Right?
Absolutely.
Yeah.
So I wanted
But
to
that's
much
a
more
prediction.
like the LHC curves than
Right.
they do
I
like
agree.
the error curves.
Ideally, one would like a step function. The only
This-
thing is, this is the best guess.
This
from
plot was
both
made by somebody who always under predicts and over delivers.
This is the conservative view of an accelerated science. You know, the question is, you can argue about the slope, but I think it is that is reflected.
No. But look at the LHC curves as
Yeah.
opposed to the error
Yeah,
curves.
but
Yes,
one
but still.
dimension is missing in this plot, which is actually the square root S. It's much easier to ramp up a very high energetic machine because you have less complication than one which sits at lower energies. And that is something, for example, why the slope at RHIC at the beginning wasn't like this and so on. So I think to say that we can reach with an EIC the same slope as the LHC, that is really requiring
The
something.
counter against that is the E plus E minus machines. It's not a true statement. The E plus E minus machines also just general,
Yeah, but
almost independent of energy. So it is true.
Let's say very nothing.
I think in the end we should both
I
challenge
think
our
we're not accelerator
accelerator
scientists.
Oh, that is
We must
fine.
be careful.
I just wanted to comment on this statement that is not much that it's really a very significant program we are. One can do already at the low velocities, which is far beyond anything that's been done. Fixed target. So a lot of the small x EA program will produce results at these velocities which will be results. So for example, diffractive structure functions in nuclei, diffractive measurements, those are day one measurements. You see something really striking or not right away. So I don't understand where that comes from. That this is a very big cross section. You see on day one, 15 to 20% of the cross section is diffractive. That's extremely very striking.
So this is a wide-ranging program, and we have to carry the community with it.
No, I'm saying the question is that
You can't just say that oh, I can do this particular kind of physics, this luminosity. So that's what.
now, what I'm saying is there's a mapping between the time scale to the ramp up with different aspects of physics one can learn. So there is physics that is day one physics, even with those luminosities, which would be extremely interesting and has never been done. Now, of course, there's physics which is also very interesting, which requires all the ramp up that you desire. But it's not that this is that one exclusively needs such high luminosity to get new physics. I think that is easy to
So I think day one versus day 100 and day 1000 is an important variable.
Okay. So we're basically giving the message to the accelerator physicists, ramp up machine fast. I mean, that's all we're saying.
I'm sure they will do that. I'm sure they'll do that. But my point is that we need to make sure that what we tell the funding agencies and Congress and those who give the money is that we can claim this result as a tremendous success in year 1, 2, or 3. If we require this, we may set ourselves up for failure. That's a risk.
I think we are now like in the discussion mode, and we do have discussion time allocated. If you allow one comment for this particular program, one of the goals that we put forward to our participants is to make sure that in the continuation of the outcome of the program, we should put the number and the outcome. So we have to be sure that we need a particular number for a particular physical goal. And this will require obviously very substantial simulations that are being done in both laboratories. I guess this is going to continue throughout the year or two after the program is done. Okay. Do you have a?
Yeah, I have a point. So I think luminosity is very, very important, no doubt about it. But if I have small statistical uncertainties, I have to control my systematics as well. And that is not necessarily the right workshop because it's not an experimental program But I think that is something which we have to start thinking about. How well can we actually control our systematic result of these measurements? And also the theoretical uncertainties, because yes, there can be made progress on things, but we discussed last week quite a bit. How well can we actually constrain a twist 3 GPUs?
Fair enough.
And I'm not saying that it is, we don't need the luminosity, but I think we should be a bit self-critical to understand our systematics and so on.
Last point before Rob comes here.
I mean, there's no question we can do science at time or luminosity. I think to some extent we should just keep in mind that we're talking about the divide papers. There is a few hundred inflows random what people ask for. People are arguing about different measurements on rubidium, on zirconium, on tensor polarization. So I think whatever we do, and then we just can't, and I agree we have to more make sure that we don't promise too much. On the other hand, we all envision the EIC as I think a science program of a few hundred inflows random.
Right.
So in the end, we just got to shoot for that. I think we should just push our accelerator people to think about why can't the ramp up be faster, and let it give them homework to do. Sounds okay.
On this positive note, let us thank Bernd once again.